Good afternoon and welcome to our third webinar from the REALISE project, which is called it's about the Cork Cluster study. My name is Philippa Parmiter and I'm from Scottish Carbon Capture and Storage, and I lead Work Package 5, which in the REALISE project, which covers dissemination, data management and innovation. So before we get started on the actual content of the webinar, I'd like to do a little bit of housekeeping and go through a few things and run a first poll of the webinar as well, please. Next slide. So you'll have joined presumably using your computer speaker system because that's the default way. If you do have any problems, any connection issues, it's easy to join over the telephone. Just select phone call in the audio pane and then you get the dial-in information. So you can always join by phone if your internet connection goes down. So throughout the webinar, we'll be interested in hearing your questions. So please enter these in the questions box, which you'll find in the panel. And we will monitor these throughout the webinar and they'll be answered in the Q&A session at the end of the webinar. Any questions that don't get answered, we will capture and try to answer later and ask the participants to answer later. The webinar will be recorded and you can watch it back on our website later, which is REALISE-CCUS.eu. So we'll be running a couple of live polls. These appear on your screen, so you don't have to go and log in elsewhere. You just select the answer that you want to choose and then submit the response. So we'll give that a go now with our first live poll question. So we're trying to get an idea of who you are in the audience and what category you identify with. So are you from academia, research, or from industry? Are you more on the policy side, a policymaker? Or are you media and communications? Or are you just from the general public and interested in learning more about the REALISE project? So we'll give you a few minutes to answer those make a response to those questions. I see we've got about 70% voted so far. So in a minute, Richard will close the poll and show us the results. Okay, so that's interesting. We've got a lot of industry participants today, which is great, and some policymakers and general public as well, and academia too. So it's great to see you all here today. Thank you for your input. So I'll move on to the next slide now and hand over to Kim from SINTEF, who leads the REALISE project.
Thank you, Philippa. Hello, my name is Kim. I'm Senior Research Scientist at SINTEF in Norway. I will give a brief introduction of the project. Maybe next slide, please. Next slide, please. Yes, and then give word to my colleagues Paul Murphy from Ervia and Paola from University College Cork. Next slide, please. Yes, REALISE project started in May 2020 in the middle of the lockdown of the COVID pandemics, but we managed to produce some good results, and some of them we will present to you today. We are 14 partners in EU countries. We have 2 partners in China and 1 partner in South Korea. And our partners are distributed along the whole CCUS value chain, from development of technologies, process demonstration and evaluation of full chain CCUS value chain. Next slide, please. objective of our project is to enable CCUS deployment in full scale. And one of the main challenges that is facing many industry probably is facing now is cost of implementation of CO2 capture. So our project propose some solutions and will demonstrate those possibilities to reduce cost of the CO2 capture integrated in oil refineries or any other industrial clusters by at least 30%. And there will be different contributions to reduce this cost. It's not only energy consumption for solvent in the solvent technology, but it's use of plastic materials, it's optimal integration of capture plant into the refinery or industry cluster, or it's even more smart or intellectual process control. Everything will contribute to reducing the cost. And some of this will be demonstrated in our project. Next slide, please. We divided our work in five different technical work packages, and our methodology is to optimize the solvent-based capture technology, is the technology that we're using in REALISE project. We will optimize it for multi-stack oil refinery, which also a kind of industrial cluster with different sources of CO2. And then we will demonstrate this capture technology in a mini pilot on-site oil refinery. Then we will demonstrate same technology at larger pilot scale at SINTEF. These two demonstration campaigns have slightly different objectives. And we will also check what is the CO2, the quality of the CO2 that it produced in this process, because this is a very important part for CO2 transport companies. Next slide, please. All results that we developed in the project will be implemented in a concept that we propose for refineries to evaluate. It's a multi-stack, multi-absorber and single desorber concept, where we can have several absorbers and one or two desorbers. So, and transport through through the industrial cluster, not a gas that normally requires much more volume than transporting liquid. So this is what we will propose, and in the next slide, this will be tested then, and results will be implemented in simulation tools, which will be used to assess different cases. We have cases for Cork, which will be presented today, and we will do similar evaluation for China and for Korean cases where refineries are different size and different amount of CO2 that can be captured in those cases. And with this, I will introduce the next speaker, Paul Murphy from Ervia, who will present the studies done for the Cork cluster. Thank you.
Thanks, Ina. So as Ina was saying, my name is Paul Murphy, and I'm the lead of Work Package 3, which is Transport and Storage. I'm representing Ervia, the national multi-utility who operates, constructs, maintains the Irish natural gas and water networks, and also has a broadband dark fibre operation as well. So next slide, please. So we're going to be talking about the summary of findings from the Cork Cluster study report, and I'm dividing into three sections: the Cork Cluster itself, indigenous storage and export of carbon dioxide options, and a cost-benefit study. Next slide, please. So just for some context, please bear in mind the caveat that this presentation is discussing the findings of a report we submitted in October 2021. So there's been significant increases in materials, capex, construction costs, and fuel prices since then. Even with the COVID-related supply chain, they've obviously gone up a lot more recently with recent events in Ukraine and Russia. Next, please. So we'll start with a live poll. Do you agree that carbon capture and storage technologies are a necessary part of the technologies mix that will be used to mitigate climate change? So please select one from strongly agree to strongly disagree. We'll just have a few seconds on that. And when we're ready, we can show the results. Strongly agree. Okay, I was thinking we might have to change some minds, but I guess we will we'll just back that up, I hope, with this presentation. We shall see now. Next slide, please. So just some information on the Cork cluster. Cork is the second largest city of Ireland with a population in excess of 300,000 people. The city is contained within the county of Cork, which has a population of just over 540,000 and an area of 7,500 square kilometres. It contains Cork Harbour, which is the second largest natural harbour in the world after Sydney in Australia. And the city of Cork is surrounded by several plants, either in pharma, distilleries or in the food ingredients sector, as well as the cluster, which we're going to talk about next. Next slide, please. So the Cork cluster we're looking at are the three largest emitters of carbon dioxide in the Cork area, consisting of two natural gas combined cycle gas turbine power plants and the Irving Oil Whitegate Refinery. Also conveniently, the depleted Kinsale Head gas field is located within 50 kilometres of the oil refinery and the power plant cluster. And there's also potential future additional large emitters in an Indavar incinerator, waste incinerator, and a biomethane plant that may possibly be located close by in the future. Next slide, please. The Irving Oil Whitegate Refinery, some facts and figures on it. Crude capacity of up to 75,000 barrels per day, produces 20,000 barrels per day of gasoline and distillate of up to 30,000 barrels per day. Does a large variety of oil products ranging from the lighter fractions of LPG, propane and butane down to the heavier fractions of marked gas oil and kerosene, with diesel, various grades of diesel and petrol in between, including ethanol blends. Next, please. These are the two power plants, ESB Aghada, which is 435 megawatts, commissioned in 2010, and BGE Whitegate, 445 megawatts, also commissioned in 2010. ESB Aghada was first, I think. I'm not 100% on that though. Next, please. So this is the information on the cluster output. So as we can see, the most important figures there, I guess, are the CO2 generated in million tons per annum of the three is 2.48 million tons per annum. These figures were taken from just before the COVID event, so they would be kind of reasonable enough to use. And CO2 could be captured is 2.23 megatons per annum. And the availability then is the power plants are available 92% of the time, but the load factor, they're generating 55% of the time. The Whitegate Refinery is available 96% of the time and also produces 96% of the time, as it's a process, continuous flow operation, as opposed to the power plants, which come on and off depending on demand. The CO2 capture rate of the base case is 90% from all of these different, across all the emitters. Next step, please. Okay. Right. So now we're going to be talking about the indigenous storage and operation, or sorry, the two options, indigenous storage and export. Next, please. So the components that we're considering in the cluster study are compression, conditioning, liquefaction, interim storage, shipping, the indigenous field and pipelines. Next, please. The high-level configuration is that liquefaction and intermediate storage of the carbon dioxide will be at a single site. The carbon dioxide from Aghada power station is transported by pipeline in a gaseous phase. The pipeline pressure is fixed at 35 bar absolute, which will be aligned to the indigenous storage via Inch gas terminal, the exit point to the Kinsale Head gas field, and drying is done at each location. The density of the compressed and dried carbon dioxide for pipeline transport is 72 kilograms per meter cubed. So that is just a breakdown of the configuration of the carbon capture and storage. Next, please. The expected CO2 inlet quality. So comparing the inlet specification and the target requirement being the Northern Lights specification in Norway. The gap on the water, oxygen and nitrogen content indicates purification of the carbon dioxide is needed. The rest of the impurities would be within an acceptable level. This is based on literature data from the capture plant campaigns at Mongstad using a generic monoethanol amine. We're also looking at a different solvent in REALISE, but it wasn't available to compare just yet. So there will be slight differences. Next slide, please. So this carbon dioxide will have to be compressed. This allows for more efficient transportation, more efficient purification of the carbon dioxide. It allows for liquefaction of the CO2. So that's necessary because it has to be exported by ship in a liquid state, and also intermediate storage. It's better for that. Liquefied the gaseous CO2 reduces the electrical load needed for refrigeration and avoiding the formation of carbon dioxide solids upon cooling the gas. So here we have the plant and the parameters, the inlet temperature and the outlet temperature and pressures at each stage: capture plant, compression conditioning at the liquefaction plant, the intermediate CO2 storage before it goes to the ship or its final destination, the ship and vessel, and then the Inch terminal, which is the exit point to the Kinsale Head gas field. Next, please. So the configuration of the compressors, we expect 3 carbon dioxide compressor packages will be needed across the 2 sites, the Whitegate site and the Aghada site. 1 compressor package at each to 35 bar absolute, 1 recirculation compressor that will compress balanced gas from storage tank. That's displaced when filling tanks with liquid, evaporation from the storage tank created by heat ingress from the ambient temperature, and the flash gas formed when letting down the pressure from pipeline pressure to the 7 bar absolute, that is the intermediate storage pressure. Possible turn down to about 70% capacity with little power penalty. Below that, a bypass operation is needed. If further flexibility is forecasted to be needed, 2 or 3 packages in parallel are required. Next, please. Drying. Drying is to avoid formation of hydrates. It also avoids corrosion in downstream equipment which will be made from a carbon steel. Balance of corrosion of pipelines and joints due to carbonic acid or mechanical damage from the hydrates. And then you don't want to increase the drying costs unnecessarily, so you're balancing drying versus the damage. Compression facilitates purification of the CO2, both drying and removal of trace impurities. Adsorption or absorption method, and absorption is preferred. Low pressure steam is heating, lower electrical load, lower heat demand. Next slide, please. Liquefaction for intermediate storage and export. So in Northern Lights phase 1, it's taking medium pressure, 15 bar absolute. Future phases, Northern Lights may take medium or low pressure. Low pressure transport of CO2, about 7 bar absolute, appears to be more cost effective for long distance transportation by sea, but it's not as mature a technology. The current technology is kind of used in LPG ships a lot, so it's well understood and well used, and also for food grade CO2 transportation. External refrigeration is similar to conventional refrigeration cycles where the heat of evaporation is. It's removed from the CO2 by evaporation of refrigerant, elevated to higher temperature by a refrigerant compressor, and removed from the refrigeration loop by condensing the refrigerant by cooling with air or water. Internal refrigeration uses the Joule-Thomson effect, where expansion of gas results in cooling of the gas, allowing for partial condensation, separation of gas and liquid, and recompression of the remaining gas fraction. Slightly higher OPEX and CAPEX, pressure 70 bar A to achieve a significant liquid fraction upon expanding, and a more complex compression. Next slide, please. So intermediate storage, you can use several different types. You can use bullet tanks, stainless steel, long tanks, spherical, or floating production storage and offloading. The intermediate storage of CO2 is required as a buffer to facilitate export of CO2. Intermediate storage can also facilitate more variable production of CO2 and importation of CO2, although these have not been considered detailed in our study. CO2 is stored in pressurized storage tanks in liquid form or dense phase until the ship berths at the quay for the export. High pressure storage tanks are required to minimize the storage volumes. Next, please. So the jetty requirements. Extend the jetty head. It's a shared trestle. It was built in 1959. The jetty trestle is 720 meters long. Jetty head is 70 meters long, 370 if you include the mooring dolphins. Accommodates the insulated piping system and pipes for the vapor return. 2 loading arms will be needed for the liquid CO2, 1 unloading arm for vapor CO2. return, basically, one common spare arm, a control instrumentation system. We expect, given the high level of ship traffic, a separate jetty pier is necessary because we're expecting one ship every 19 hours. Either a new jetty or extension of the existing jetty will be necessary to facilitate export. The prospect of a new jetty was considered, although given the water depth in the vicinity, it is likely to be located very close to where a jetty extension would be built anyway. Also, the extension to the existing jetty pier option will be less costly than building a completely new jetty. The existing jetty causeway can accommodate the flow and return CO2 pipeline required for ship loading. Next, please. So we looked at low pressure, 7 bar and minus 50 degrees C, and medium pressure, 15 bar A and minus 28 degrees C. Low pressure, the shipping distance volume, the effective heel and vapor density of 94.5%, 7,500 meters cubed by 0.94. So this is the calculation. 8,200 tons is what you can transport at low pressure. Medium pressure has a higher technology readiness level because it's used today in food grade industries. Low pressure would be kind of new and unproven as yet. The weight of tank is 185% higher. The heel is 92.5%, and you'd be talking a 7,200 ton ship. The shipping requirements for the cluster were reviewed with the conclusion that the total travel time and ship size determine the frequency of the ships required to transport a given flow rate. Given the assumed size of the ship of 7,500 meters cubed, 10 vessels will be required, with a ship calling at Cork Harbour every 19 hours. Next, please. The indigenous option at the depleted Kinsale Head gas field. So Kinsale Head gas field produced from the mid-1970s until 2 years ago. It has 300 million tons carbon dioxide storage. It's currently being decommissioned. It's partially complete. As you can see, there are a number of fields joined together out at sea. Bravo and Alpha platforms. Potential to reuse. So 50 kilometers of pipeline from Inch Terminal there on land at the southern part of land to the field itself. And then there's 10 kilometers further of pipeline from Inch Terminal to Whitegate, which is to the north of Inch Terminal. There's limited opportunities to repurpose though. There's potential to repurpose the 24-inch diameter offshore pipeline for CO2 transport to Kinsale Head gas field in gas phase only. It would need a new pipeline for liquid due to the age of the pipe. In addition, there are some sections of the now redundant natural gas network which could be repurposed for CO2 transport. The existing Kinsale Head gas field platforms and wells are currently being decommissioned. Similarly, given their age of 48 years, condition and design life, they offer little scope for repurposing. Next slide, please. Indigenous gas phase, maximum flow rate of about 40 kilograms per second, 3 wells, 2 platforms, 80 kilograms per second, about 2.5 million tons per annum with 50% spare capacity. A minimum flow rate for the wells of about 30 kilograms per second each. Low flow, single well or lower pipeline pressure. Half available storage capacity for operating gas phase. 2.23 megatons per annum, million tons per annum, more than 50 years worth of injection capacity. To avoid frequent shut-ins, there are 4 options. Line pack, which is better with gas phase. Buffer storage of about 40,000 meters cubed of liquefied CO2 would be needed to provide a flow rate of 30 kilograms per second for a duration of 400 hours, which is a large amount of storage, so possibly the other options would be better. Changing pressure in the transport pipeline or using wells with different operational windows. There's a significant additional capacity to accommodate CO2 from other emitters in Ireland or elsewhere. The studies also determined that initially CO2 be injected in gas phase. As the pressure in the reservoir gradually increases over time with continuous injection, the switch to inject liquid dense phase CO2 will come as the reservoir pressure rises to meet the injection pressure. It was determined that up to 3 new injection wells of 7 inches would be required for injection along with the associated infrastructure. Next, please. Now, the third part, the cost-benefit analysis. Next, please. So the cost of CCS has been reducing. It started at $100 US per ton at Boundary Dam facility back around 2008, 2004. 65 tons per annum in Petronova facility, which was 3 years later. Then $43 per ton. Which are facilities which are due to come into operation in 2024 to 2028, and then forecasted to $33 US per ton. New technologies at pilot plant scale promise capture costs around this. Next slide, please. The assumptions or inputs for our cost model are target internal rate of return of 3.4%, insurance and local tax 2% of capex, working capital 5% of the product level, debt equity ratio of 70-30, straight line depreciation over 25 years. The input costs come from public domain data from Wood CCS benchmarking project for BES, the UK department, of CANSOLVE next of a kind unit. And then the base case, 2.48 megatons per annum CO2 produced, 2.3 million tons per annum CO2 captured, 4 years in development, 4 years in construction, gas phase injection, liquid phase being exported, and all new infrastructure. Next slide, please. So these are the forward curve prices from the International Energy Agency, which came from 2021. But they're well out of date even now with the current events in Russia, etc. But basically the story is going to be the same even if you did it today, which is we're expecting the carbon price to go up, and this is for natural gas, but basically the pence per therm price of natural gas on the forward curve is that it starts to decline around 2040 due to more renewables coming on stream, more hydrogen, etc. crowding out, substituting is the word, natural gas, and that is generally what's going to happen, even though there's been a major spike in the price with current events. Next, please. So on capex cost, so there's a lot of numbers there, but basically the cost benefit study examined both the option of developing a carbon dioxide storage site locally and exporting the carbon dioxide to a storage site in Norway, each under a similar range of production levels in the relevant emitter sites. It was found that in the two scenarios of export and indigenous, they vary in their capital and export and operating costs. The outcomes for the cluster, including the three largest emitters, would avoid up to 2.23 million tons per annum carbon dioxide emissions per year in the base case scenario. So there's the differences on the table. And next slide, please. The OPEX is up there as well. Total costs on the export, total cost. Let's see, yep, that's comparing them again. And next slide, please. So this bit is about comparative levelized cost of electricity. Levelized cost of electricity is where you have different types of generation between wind and gas and nuclear and so on, and you're trying to bring them to one level to compare them with each other. Essentially, it's like net present value does with time-based cost factors. So in both scenarios, the higher load factors in the emitter plants will result in lower abatement costs. While the export scenario requires significantly less capital investment, the indigenous storage development is much more economical over the lifetime of the project. A key factor here is the cost of shipping and receiving carbon dioxide overseas. That was the major finding from a cost point of view. Next, please. And then just to add in, a number of the expert bodies agree that CCUS is a necessity, not an option, calling back to our poll at the start. The IPCC, CCUS is critical to achieving climate targets, 130% higher cost without CCUS. Airgrid, which is the Irish electricity grid operator. Tomorrow's energy scenarios, CCUS is deployed in 2 of the 3 scenarios. Climate objectives are only met in the scenarios which deploy CCUS. The International Energy Agency, without CCUS transformation of the power sector, power will become $3.5 trillion more expensive to generate. And then the UK Committee on Climate Change's NERO's Net Zero report of May 2019 states CCUS is a necessity, not an option. Last slide, please. And thank you very much. That's our last slide for this section.
Hello, everyone. Yeah, I hope you can hear me well. My name is Paola Velasco. I'm a postdoctoral researcher at the Clean Air Production and Promotion Unit at the University College Cork, and where we do work on people's relationship with the energy system. So far, we learned about the REALISE project, the industrial cluster in Ireland, and also the role of carbon capture and storage in the energy transition. Now for this presentation, I will be discussing the importance of engaging the public when planning a CCUS project. And we'll finish by providing 5 principles that can make social acceptability a little bit more easily achieved. So next slide, please. Yeah, so the technical and geological aspects of CCS are, of course, the primary focus on planning and implementation phases, as we already saw in the last presentation. However, REALISE recognizes the importance of understanding and appreciating the social context of prospective CCS projects. We therefore have a specific work package that looks into the societal, sociopolitical, and commercial context of CCS deployment. Next slide, please. A recent analysis, as Paul already mentioned, they do say that CCS is a very, very important to meet decarbonization goals. However, local opposition is often cited as one of the reasons of why is it that CCS is not being able to be deployed as planned, so causing some delays and even cancellations. Therefore, this experience has shown that CCS to be widely deployed necessarily needs community support. In general, effective community engagement is important for relatively new technologies such as CCS because people have a lot more questions and concerns than other established industries. And in the case of CCS, this is particularly important because of its perceived links to fossil fuels, which can provide further complications that require additional engagement efforts than other industries such as renewables. Next, please. And next, please. Sorry about that. Next slide. Yeah, so why is it important to engage the public? So engaging the public, it's really useful for identifying risks, also improving project design and establishing ways to resolve communities' concerns about the project. In turn, these benefits may contribute not only to the individual project's outcome, but also to the long-term perception of CCS and also the developers. In short, when seeking CCS technologies, it is important to engage communities in the process of planning, design, deployment, operation, and maintenance of the project, not only because people have the right to be included, but also because its engagement will be very, very important to successfully deploy CCS. Next one. So what exactly is public engagement? Well, it can be defined as the process through which a project developer or a regulator builds and maintains constructive relationships with communities by involving them in a timely and transparent manner over the life of the project. This engagement can take many forms. Some are more passive processes where communities ask questions and then developers simply provide answers. And there's also other more proactive processes in which communities actually co-develop the project or even own it financially. And within this, like, who is exactly the community? Well, the community is usually the people that live near the CCS project and could be potentially affected by it. It's important to know that these communities are not kind of like, homogeneous, needed communities, but actually it's a diverse collection of interests and stakeholders who might actually see CCS in different lights. Next one, please. So, okay, so let's go into, 5, of course, there's many more principles, but 5 that we would like to share with you during this presentation. We gathered this 5 through going to a really thoughtful literature review. We also did case study analysis and interviews. And well, the first one would be to, yes, understand the local community and also the existing legal requirements. This will give you information about how is it that it's best to engage and when to engage. One way of understanding the local context is to do a thorough social characterization assessment of the community to understand leadership dynamics and decision-making processes. We also need to consider the community's previous experience with the developer, the investors, and also the community's history with other industrial projects. A community's previous experience with public participation and also the level of awareness about climate change, it's very important for consideration as well. And finally, it's important to ensure that the public engagement processes reach different subgroups within the community, so not only those that are already participating. Next slide, please. So the second principle is within the exchange of information, it's very important that this is a transparent and inclusive process, which includes a proactive dialogue between all stakeholders. This information can include facts about CCS, the description of the project at hand, and also the ways in which it can affect the community. And this information can be, of course, shared in different ways. This includes, for example, public hearings, open houses, focus groups, and one-to-one meetings. But it's important to know that not only formal channels of communications have to be established, but also informal ones. Of course, ensure that the content is clear, easy to understand, and tailored to the different subgroups within the community. Next slide, please. And the third principle is to identify what would be the best level of engagement. Of course, there's a one-way communication exchanges. These can be quite useful for certain situations. However, two-way communications such as consultations usually lead to a deeper level and more productive levels of engagement. An extra step beyond consultation is a negotiation, which incorporates elements such as joint decision-making between project developers and the local community. This deeper level of engagement is usually employed when the community has a formal authority of the given issue or project, such as, for example, if they own the land where the project will be installed. Next, please. And the fifth one is to discuss the potential impacts of the project. So as if any other industrial activity, CCS project will have specific impacts, and this could be very diverse. For example, it could be the number of jobs it brings to the community, maybe if it has any effects on the local economy, health and safety, the environment, such as, for example, the effects on soil, air, and ecosystems. So providing an ongoing forum for exchanging information and discussing these risks and benefits of a proposed project should be really, really central when engaging the public. Next slide. And finally, the fifth principle is to know that you really have to continue the engagement throughout the project life cycle. So in a way, public engagement of CCS should not end like as soon as you have a successful initiation of the operational phase of the project. Instead, effective public engagement will involve a community's input and multi-stakeholder dialogue throughout the project. So even when you're doing the feasibility studies and site screening, and then continuing it into the post closure of the project itself. And next slide. So just kind of like a final word. Engagement techniques that focus on community concerns, which are transparent, realistic, and honest in the way they can deliver, fall into the category of good practice. So this is what one of our case study informants mentioned. We thought that would be really nice to share. Well, hopefully this will give you kind of like a overview of what is it that we need to look at when thinking about the social context of the CCS projects. Thank you very much, and look forward to your questions.
Thank you. Thank you, Paola and Paul. Thank you to the panelists for your presentations. We are now going to begin answering the questions submitted during today's webinar. As a reminder, you can still submit questions through the questions panel in your attendee control panel. Do we have any questions? Maybe panelists can also turn on cameras. While we are waiting, Paul, may I ask you, what is the main challenge for full-scale deployment of CCUS in Cork or in Ireland? Are you muted?
I suppose it's the industries themselves and seeing a need for it and to invest in it. So the oil industry is obviously going to see that more than some other industries. The power plants, they may choose to, because the oil industry is going to continue producing diesel, petrol, kerosene, etc., and carbon dioxide is going to be produced as part of that. The power plants may choose to move towards more of a hydrogen blending, but if they stay with methane, and when power plants are built, coal and natural gas power plants, they're going to have a 50 to 60 year lifespan anyway. So some part of that will probably have to be weighted with carbon capture. And I suppose then you have other industries like cement, particularly, which produces a lot of carbon dioxide as part of its as part of making the product, and that's just part of the chemistry of the product. It always will produce a large amount of CO2 that will have to be abated. Things like iron and steel making, things like aluminium making. So the cement making does happen in Ireland, distilling happens in Ireland, but cement making, steel making and iron making is not something that happens in Ireland, but it does happen in other countries. So it's the local industries seeing the need for it.
Thank you very much. Paola, have you already started the discussion information with the local community? Any initial feedbacks?
So we started looking at the context just so far. So we started looking at, kind of like social demographics, understanding what is, the industrial history of Cork, etc. So we're kind of like going into that first to then see how is it that we can better engage the different stakeholders, and which stakeholders to engage really throughout the project, of course.
Thank you. And one more question for you. Has the Irish government engaged with the topic of CCS up until now?
To my understanding, it has engaged to a certain extent, but not fully, completely as we would have expected in a way. So we'll see maybe that changing in the coming months of years. But yeah, I think that was going to be a really important role of the project, to be able to engage the government more.
Thank you. Paul, next question is for you. Have you considered higher capture rates? Best available technologies in the UK is 95%, with 99% plus looking likely to be economic.
I suppose we were trying to, again, this report was over the last kind of 2 years it was made, before the end of last year. So we were looking at what was feasible then, and 95%, yeah. I mean, we were trying to make a base case that wasn't too far out of the bounds of possibility, because we're trying to prove a feasibility. If we were to look at it again, with the way technology has moved on, we could possibly look at 95%, but it's a good kind of starting point, I think, with a realistic kind of starting point.
I can also add on this, comment on this, 95 and 99% plus for solvent-based capture technology there is a possibility for this, and we will definitely test this in our demonstration campaigns and see what will be the output, and what will be maybe the additional cost for that. So results will come. Just follow up our project.
Yeah,
there is one more question.
I should have mentioned that as well, that we were using the generic solvent. So if we were using the new solvent, we could up it, as you say. So with what the solvent that was there, 90% was more feasible.
Yeah. Paul, one more question for you. Is there any thoughts or plans to monitor the flow distribution of the CO2 once it's injected into the storage reservoir? You're muted again.
Could you just ask that one more time, Inna, please?
Is there any thoughts or plans to monitor the flow or distribution of the CO2 once it is injected into the storage reservoir?
So there is actually a carbon capture and storage directive at EU level that gives you a regime that you must follow to monitor these for environmental reasons after it's been injected. So at a minimum, we're going to, if whoever injects carbon capture and storage in the EU is going to have to comply with that monitoring regime. So, yeah.
Yes, and there are technologies available for this. One of our partners in the project, Equinor, has a lot of experience on this. This can be also discussed and will be discussed. And also, if CO2 is to be stored in Northern Lights, then these technologies are in place already. And for Irish, if it's local storage, there will be definitely requirements and technology that will be used. Yeah, thank you. Do we have more questions? Okay, so there is some more. To Paul, are there plans to capture the excess amount of CO2 of 0.25 million ton? What's your approach to what needs net zero? Also, do you plan to utilize green sorbents rather than conventional systems?
Again, I guess this feasibility study was looking at a realistic kind of case. So the final capture, again, as Ina was alluding to, with the new technologies we're looking at, that may be possible. When we move from a feasibility study to the front-end engineering design and then the detailed design, that'll become kind of clearer, and we'd be kind of aiming for that. The green sorbents, I'd imagine, yeah, there'll be a push on for that if there's a choice. Most companies are going to go for the sustainable option in today's environment. And you know, the whole point of carbon capture and storage is to be more sustainable. So I'd imagine the sustainability case will be important there and will lead naturally to choosing the more environmentally friendly sorbents.
Thank you, Paul. Any last remarks to the audience, Paul or Paola? No?
Just thank you for your questions and attention.
Okay.
Yeah,
then
thank you very much.
Thank you. Then we have come to the end of our webinar. I would like to thank everyone for attending today, the presenters and organizers for making this possible. Once you leave today's session, you will receive a survey on the presentation, and we would appreciate if you would complete that and provide your feedback. We will also receive a follow-up email within 48 hours with a link to view a recording of today's webinar. On behalf of all presenters, thank you for joining us today and have a great rest of your day. Thank you.
Thank you.
Thanks.